Good day everyone, and welcome to week 6 of the differential equations class. Here is the plan for today's lecture, and we have two main goals today. So the first is to finalize the solution of a homogeneous second order ordinary linear differential equation with constant coefficients. Right? And the second case is to look at what we can do in the case of a non-homogeneous second order linear differential equation. So in order to understand today's lecture, you've got to review certain topics. Well, note that they are quite diverse. So complex numbers, we're going to use complex numbers today. Linear systems of algebraic equations from linear algebra, also very important. And of course, you need to review the previous week. Let me quickly recap the material of the previous week. So here is the most general form of a second order homogeneous linear ordinary differential equation with constant coefficients, right? So recall that the fact that it is homogeneous means that this is 0. Constant coefficients means that these a, b, and c are some real numbers. Well, and linear means that it is of this form. In order to solve it, we set up the characteristic equation, and then the characteristic equation is just a quadratic equation, so very often it has two real roots, and then we can construct a solution of the corresponding ordinary differential equation. Recall that we have also this notion of the Wronskian of two functions. So this is a certain determinant composed of these two functions. So the Wronskian can be used to test whether two solutions of a second order differential equation are linearly independent or linearly dependent. Right? So anyway, what we don't know yet is what happens if either we have a multiple root or complex roots. Then a very important result from the previous week is that the set of all solutions of a second order homogeneous linear differential equation is a two-dimensional vector space. Well, but with two-dimensional vector spaces, it means that there exists a basis of two elements, but generally speaking, there is no obvious standard choice of a basis here. Right? And then if we have any particular basis, it's just like in any vector space. If we multiply our basis by an invertible matrix, then we get another basis. Right? Recall that this is a general theorem, so it works for equations with non-constant coefficients and for equations with constant coefficients. It's just that for non-constant coefficients, usually it's impossible to actually find solutions. But the theoretical theorem is still true. So here is an example of how this theorem can be applied. Note that here the characteristic equation is r squared plus 1 is 0, so the roots are complex numbers. So we haven't learned how to treat such cases yet, but you can guess that the possible solution is cosine t, another possible solution is sine t, but also at the same time there is another combination of solutions. And let me show you that it is indeed a basis, right? So the fact that this is a basis, you can compute the Wronskian. We did it the last time, and maybe let me remind you that the Wronskian of these two functions is the determinant. The first row is cosine t, the second row is sine t, and sorry, the first row is cosine and sine, the functions themselves, and the second column is the derivatives of these functions. So it's minus sine t and cosine t, and the Wronskian is going to be cosine squared t plus sine squared t is 1. So and generally speaking, the Wronskian of two solutions of a second order differential equation is either 0, and then the solutions are linearly dependent, or is never 0, not for any value of t, then solutions are linearly independent. Also, but notice that we can construct the second basis from the first basis by multiplying with this matrix 1 over square root 2 1 over square root 2, 1 over square root 2, and minus 1 over square root 2, and the determinant of this matrix is actually -1, so this is an invertible matrix, and indeed it means that